What we have now are n squared equations that look like this in n squared unknowns, one for each mesh point. And what we would like to do now is translate this into matrices and vectors. Now here what I've done is I've already written down what the vector is and what the vector of the values of f are. And what I want to determine is what my matrix here looks like. And these are rows and columns of the matrix, and remember that we end up doing some value here times that plus a value here times that and so forth. And if you think about it, if I is equal to 0, then these two values are equal to 0. So we end up with a 4 times epsilon 0. So we end up with a 4 right here on the diagonal. Then we end up with a -1 right here. And if we only have 4 mesh points in each direction, then the next non-zero comes from the fourth unknown here, the fourth position. And that is a -1 as well. And anything that I don't put in here is a 0. Okay, then we move on to the next point. Now I is equal to 1. So what we get is this is 0, but this gives me a -1 here. That's for 1. And then 4 -1 -1. Let's rewrite this here again. 4, 5, 6, 7, and so forth. Okay? We go to the next one, and what we get is -1, 4, -1, and another -1 here. And then we end up being here on the end, and therefore we get still one more -1 and 4 here, but there is no point to the right that's equal to 0, but we do have a point above. All right? Then we get to this point right here, and we get another -1 from here. We get a let's see, the point to the left is now equal to 0, so this one disappears, but we get a 4, and then another -1 and a -1. And notice that it's starting to look a little bit difficult here. If we put a bar here and a bar here, then it tells us where we got to the end of a line here. And what that really means is that all of the unknowns up to this point correspond to this first line, and then we start over again with another one. Okay? And what you notice is that there's this very distinctive pattern here, etc. And notice we can put another line here, because that's the end of the line. Or I shouldn't have put it there, but you get the idea. Okay? We got a bunch of -1s here. We got this very distinctive tridiagonal matrix here. And here we also would get yet another block of -1s. What do we notice about this? Well, first of all, it has this very distinctive pattern where we end up with 5 diagonals that are non-zero, although they're not all clumped together. There's a big block of 0 sitting right here. We also notice that this matrix is extremely sparse. Right? There are a lot of zeros here, so you wouldn't want to store all of those zeros, nor would you want to compute with all of those zeros. You'd want to somehow take advantage of them and see whether you can reduce the amount of computation that you end up doing. And we notice this link to the actual equations that gave rise to it. And it turns out that you can take advantage of that as well. So now you understand a little bit of where sparse matrices come from and what kind of special matrices might come up in practice.